Okay, here we are. Today we're going to talk about some more details on some different equipment available for GMA, a little bit more electrical terms, more specifics there, and then get into some electrode specifics. So first in chapter 3, a little bit more about our equipment possibilities. Of course, you have to have the power source. Everyone's familiar with that now. So the things that the power source controls would be the input voltage, also called primary voltage, the open circuit voltage, output ratings and performance, and then the duty cycle. So these are some issues we're going to explore a little bit more. So the input voltage, that's pretty simple. That's, your electricity going into your machine. Generally, you have 110 or 220, both single phase. Of course, there are welders that can work on three-phase, but these would be the most common, and these are the two that we are using at OCC. So that's your input voltage. And then open circuit voltage, that is the voltage output range of the power source before the arc is established. And the only time, at least on the welders at OCC, that you're going to sort of encounter this would be when you use the V-Sense feeders, and everyone's used those by now. And you'll remember that there's two numbers that flash up on the screen on that. The larger number, that is the output or the open circuit voltage. So that's basically the kind of available power before the arc actually starts. And then when you pull the trigger, the arc is actually established. So the open circuit voltage, the amount that you have available to you, that affects how the arc will start. That's why it is important. And then the output ratings and performance, the actual performance of the welder, is also controlled by the power source. So the output is the voltage and amperage used when the current is flowing, what happens when the trigger is being pulled. And then the performance would be how the machine actually welds. Also, these things are both controlled by the power source as well. And then the last thing we're going to talk about related to the power source is the duty cycle. So the duty cycle is the percentage of time in a 10-minute period that a machine can run at a rated output without overheating. Sounds a little bit more complicated than it really is. So every 10%, you'll see a duty cycle in a range from 20% to 100%. So every 10% represents 1 minute of operation, okay? So a 20% duty cycle can weld at a specific output range, a specific voltage setting for 2 minutes without overheating. A machine with a 100% duty cycle can continuously weld at that output rating, 100% of the time, constantly, basically. So it doesn't overheat. 50% means that it can weld, 5 minutes out of every 10, and then you would have to stop. And the reason why why you get the different duty cycles, it depends on these different aspects of the power source, the size of the internal wiring, the type, the quality of internal components, insulation of all of these components, and then the amount of cooling that might be required and available to you in the machine. So there's basically, for duty cycle, there's 3 different classifications. Your class 1 is from 60% to 100%. That's your heavy industrial use machines. Class 2, 30%, 40, or 50% light industrial. And then class 3, 20% would be home or hobby use. So the internal components basically of the machine determine what your duty cycle is going to be. The duty cycle is usually marked on somewhere on the outside of the machine. It'll tell you what the duty cycle is at the specific output rating. But if you think about it, you don't necessarily have to have a machine that's 100% duty cycle. Think back to the last Friday when you were actually welding in class, and remember, that you're not actually welding for 10 minutes straight. pretty much ever. You weld for maybe 1 minute on your weld, then you look at it for a couple minutes, you maybe have to get new material, prepare your new material, clamp up your new material. So there's lots of space in between the actual welds. So especially for doing like in-shop kind of fabrication, you don't actually hit that duty cycle as often as you might think. If you think about the kind of welding that's actually done, in most everyday situations in a fabrication shop. Of course, if you are doing like heavy duty industrial welding, then you're going to need the bigger industrial use machines, the class 1s, and it's just the different classes, as you might easily imagine, are going to be different price ranges. So you'll have to decide what exactly you need and what you need to have to pay for if you're choosing your own machine. So that's the power source here, the power source controls there. And since we're talking about electricity a little bit in that, I wanted to get into a little bit more technical and kind of aspects of the electricity that you're interacting with as you weld. So this one term that you might have encountered already, especially if you've done any TIG welding, is inductance. So inductance is the property in an electrical circuit that slows down the rate of current rise. So it affects how fast the current goes from 0 to 20, say. And how this affects welding is that it affects the separation of the molten drops from the electrode as the current squeezes the electrode. Hopefully you can remember a little bit when we did spray transfer. We tested out the spray transfer welding on the welder that I set up. And you can see, I find it a lot easier to actually see how the metal is separating off of the electrode in that transfer mode. You can really see that pinch force being applied and kind of the end of the electrode wire getting kind of thin and pointy like that. So that's because of the inductance that is happening in your welder. So sometimes in some welders, you will have inductance control. Not on any of that's not true. On one of the MIG welders that we have in the shop, you have inductance control. That would be the Lincoln 210 MP, that new digital one with the fully digital interface. That actually does have an option for inductance control, but none of the other welders do. So for MIG, it's not necessarily as important, but obviously it's nice to be able to have that control. If it's available to you, to be able to choose that control and set it up yourself. So if you do have it somewhere, going to be on the main panel, accessible on the main panel, just like your voltage and wire feed speed are. So for GMA, you use it in short circuit transfer. In flux core, it doesn't actually affect how the electrode melts. So that you don't have to really worry about it if you're welding with flux core. But the basic kind of idea or rule as far as thinking about inductance and inductance control is that as the electrode diameter increases, you move from your 0.225 to your 0.35, the amount of short circuit current also increases with the diameter increase. The bigger the electrode, the more short circuit current you have. And therefore, the ideal amount of inductance increases. So the larger your electrode diameter, the higher the ideal amount of inductance is. So again, a little bit more on how it affects GMA in short circuit mode. So high inductance, maximum inductance, turned all the way up to 11, if you will. That means it's actually a slower rate of current rise. It means it goes when you set it to 15 or something volts. That means it's going to go from 0 to 16 a lot slower if you have a high inductance. But that actually means, how that translates to your actual weld, that means more penetration and a more fluid weld pool. You get a flatter weld and a smoother bead. That's with more inductance, meaning a slow rate of current rise. So if you have maximum inductance, or minimum inductance, I'm sorry, I'm going to confuse you. If you have minimum inductance turned all the way down, that means the current rises really quick, goes from 0 to 15 really quickly. That is going to give you a more convex bead, probably going to increase the amount of spatter, and it does have a colder arc. So again, as with pretty much anything else we discussed, there's some times when these qualities, a more convex bead and a colder arc, might be more desirable than having a flatter weld and a smoother bead. For instance, a colder arc would be better on thinner material, right? So you might turn your inductance down so you get a quick rate of current rise there. So inductance, that's a little bit about inductance. To continue our little dive into electricity terms, other things you're going to hear talked about or discussed would be arc voltage and slope. This is really getting into the electrical side of things here. So arc voltage is the voltage output when the arc is present. When you got the trigger pressed, that is the arc voltage happening right there. Now, slope, the term slope, that is the slant of the volt-amp curve. So that I'm going to illustrate that in the next slide. I got a picture of it, but let's try to talk about it first. So that illustrates this slant of the volt-amp curve, illustrates the operating characteristics of the power source under an electrical load. Under an electrical load means when you've got that trigger pulled, when the arc is present. Now the slope is automatically set in many machines, in most machines, in fact. And on most of the machines that we have at OCC, you don't have any ability even to address the slope. We'll just talk about it because some of the newer power sources and newer machines do start to have more of those controls available to you. For your information, just to kind of store in your mind, FluxCore operates best in a flat mode with a flat slope. So again, to try to illustrate what this means, here's our pictures here. So this is the slope in a constant current power source. Constant current is what we use for stick welding and for TIG welding. We, remember, are using a constant voltage power source for GMAW and FCAW. So the slope here with the constant current, you see this dashed lines are the ranges of the amperage. So remember that current equals amperage. So that amperage is not fluctuating very much at all. And then the voltage is fluctuating much more. And the operating point here is where these two meet, basically. And then for constant voltage, what we are using in this class, you've got a much flatter slope. And you see in this one, the voltage between these two dashed lines, this is what, for all intensive purposes, does not fluctuate. And then this amperage has a much wider fluctuation. Remember, the current, depending on the wire feed speed, you're closest to the base metal, and all of these other things make the amperage or the current fluctuate a lot more. But you set that voltage, and your machine keeps it at that voltage because you have a constant voltage power source. So this is what is meant by slope. This is what it actually looks like here. Now, that was a lot about electricity and related to the power source and stuff. We're going to talk about a little bit about some other additional equipment that you have available. This would be, again, in newer stuff, newer equipment that you have available out there would be pulsers and auxiliary pulsers. So you remember we talked about deposition modes, and you have spray transfer and then pulsed spray transfer. So if you want to do pulsed spray transfer, you have to either have a machine that can already do that built in, or you can buy these auxiliary pulsers basically and attach them to a currently existing machine. And then you can still adjust and set those pulse times. So that's a possibility for another additional piece of equipment. And then, of course, our dear friend, which you've already used, the V-Sense feeder here, those suitcases that are up on the wall there. And I know we've talked about this at different times in class as you've used them and stuff, but I just wanted to set this out there and sort of make sure we outline it and go through all this. So a V-Sense feeder, if you use it with, it can use on both power sources, constant current or constant voltage. So when you use it with a constant voltage power source, you set it up as it's basically an external wire feeder. So we are using it in this way with a constant voltage power source just as a regular old external wire feeder. So our shop power sources, right, can be set to constant current or constant voltage. So you could switch it up and have the machine use it as a constant current machine. And then you have to flip a switch an internal switch in the V-Sense feeder itself. It's kind of in the back there. If you want me to show it to you in class, then I can show it to you. And then when you use it with constant current, you have to have the thing that extra clip up top does. Remember, that's not the ground. That's this extra clip that senses the voltage, and then it feeds the electrode at the proper rate for that voltage. So because this constant current power source is not, you don't actually, if you have a constant current power source, what you are controlling is the amperage instead of the voltage. So you would set the amperage, and then that extra clip senses the voltage that's occurring and feeds it back through the machine and then through the V-Sense feeder to tell the electrode to keep that right rate to keep the voltage that you want it to have. So it's just like kind of an extra step. And remember, this is useful because constant current is the power source that's already used for stick and for TIG welding. So if you had a constant current power source out there in the field or in your shop or something somewhere, instead of buying a whole new welder in order to do GMAW or FCAW, you could just buy these V-Sense feeders, hook it up to the power source that you already have, and use it. So that's the reason why these were meant to, why they were built and why they can be useful. All right, some more of the equipment. Since we just talked about the V-Sense feeder, we'll get into other wire feeder options, a little more specifics here. So you've all encountered and seen now these drive roller systems and the different welders that we have. We've talked about this at different times. Just a reminder, the grooves in your drive rollers have to be the right size for your wire. Some of the drive rollers will have multiple grooves in them. Some of them you have to take one out and put another one in. If you want to take a look at that next time you're in the shop, and see what kind of machine you happen to be on that day, it's kind of a good little thing to check out. And we've talked about this too, not over tightening the drive roll tension. It's a common error because it seems like, you want to be nice and tight and, hold everything tightly. But if this is over tightened, that is going to make this sort of bird nesting issue more of an issue, because if there is something at the other end, at the gun end of your welder, and, you fuse the electrode to your contact tip or something like that, if those rollers are a little bit looser, then when you pull the trigger, it can basically just slip in those rollers versus trying to, having it really pinched tight and pushing it through this way when it can't keep going this way, and then it'll just start feeding out to the side and getting a big mess in there. So now some more of the drive roller options, like I was saying, you can have sometimes 2 grooves, sometimes 4 grooves. The rollers themselves can be knurled, they can be grooved, or they can be cogged. You can have a V-shaped groove, you can have a U-shaped groove, and some of these are going to be different. You're going to need to use these differently for different electrode wires. And then everything that we're using is a push type wire feeding system. It's pushed from the drive roller all the way through to the end of the welding gun. There are some other systems out there. There's a spool gun, and then there's a push-pull system. So the spool gun, this is generally used for if you're using softer wires, like doing aluminum or possibly bronze. You have this short gun here and a small spool. There's a motor inside this little spool gun, and it drives, when you pull the trigger, it pulls from right here and the wire feeds just right from this small spool right through this, straight shot out the gun. So for a softer wire, you want to use this because a softer wire is not going to be able to feed all the way through that gun just from being pushed back here at the drive rollers. It's not going to make it all that way. So you can just have a nice short little movement, right from this tiny spool all the way out to the end of the gun, and then you can weld with the softer wires. And then you have sort of a more advanced version would be a push-pull system. So this is a look at a push-pull gun, and we have these in the shop. I am going to set up one of these for welding aluminum for us. So it pushes back here it pushes at the drive rollers. It pushes the electrode, feeds that big spool just the same as normal. But when you pull the trigger at the same time as it's pushing from the drive rollers, you have these extra rollers up here that also are pulling it up here and pulling it and then pushing it out to the end of the gun right there. So that gives it's just a little extra help so that it doesn't have to just push, all the way from the end of the gun. It keeps it straighter and from kinking up and stuff in there. So those are two other systems that you can purchase. You're not usually going to get them coming with a specific welder. You have to purchase them separately. And then a little bit more about the wire feeders, especially the maintenance. If you're doing this yourself, if you have your own machine or you're working for somebody else, obviously it's electrical components. You want to keep it dry, as with anything electrical. You are very highly recommended to have an electrician check it for any electrical malfunctions. It is a complicated electrical machine. Make sure that you use the right parts. So if you're replacing anything like the circuit boards, it's good practice to inspect the guides and the rollers often. Replace them when they get worn. Blow them out with compressed air occasionally. You don't want it to become super clogged with particles and have just get messy in there. It's always good to keep it kind of as clean as possible. So now we've talked about wire feeders. Here we're going to talk about the electrode wire itself, and a little bit more about the manufacturing processes for GMA and FCAW electrodes. So first, the manufacturing of GMA welding wire. So first, the material is made into a large coil of heavy wire while hot. The process is called being hot drawn. It's drawn through smaller and smaller dies until it gets to the size that you're trying to get it to. And then it's reduced again and again and again until you get to the specified, 025 or your 035. And then it's annealed and cleaned. So annealing is softening the metal by heating and slow cooling, or controlled heating and cooling, basically. You can't have the material be brittle. Obviously, it's in a round spool. You don't want it breaking, snapping when it gets bent. And it has to be fed, nice all the way through that the lead line there. So you don't want it to be brittle anywhere in there, so it would break off. And then some materials like stainless steel electrodes, they have to be annealed several times. So some electrodes take more work manufacturing than others. Now for flux core, those are different. Those are not just a solid wire, right? That's a hollow tube filled with flux. So the flux mixture itself, the inside here, consists of deoxidizers, slag formers, arc stabilizers, whatever the manufacturer is putting in there to get, what they're trying to get with this particular electrode. The base material itself, it's first formed into a U shape, and then it's filled with a flux, and then it's drawn through more dies until it's sealed into a tube, and then it's drawn through more dies until you get to the desired size. Now, this part is where there can be lots of letters and numbers, which seem a little bit intimidating. We are not, for the purposes of this class, trying to memorize every single possible electrode, or even every single thing that every number means. But I do want you to be able to recognize different kinds of electrodes and recognize generally the information that's being provided for you, or at least know what you need to do to find that information. So the first letter here, that's electrode, E for electrode. And then the R here, that R is for rod. So that means the electrode is a solid rod, which can also be used as a filler rod for TIG welding, for instance. And then you have two numbers here, represented rather by the two X's. So these two numbers in the middle are to designate the minimum tensile strength in thousands of pounds per square inch of the deposited weld metal in a specific test weld made with the electrode in accordance with specific welding conditions. So that's generally this is your tensile strength here. And then S here, this last letter S is for solid electrode wire, sort of similar to the R for rod. And then you have another X here, another number, and that is going to tell you the specific alloy and deoxidizers that make up the electrode's chemical composition. So the actual sort of alloying elements that are in that the material there. And then for flux core electrodes, and this is for carbon steel, both of these are for carbon steel. So flux core electrodes, the first thing that you should recognize is that there's no R here. It's not a rod. Can't use it for TIG welding. And then there's a T here at the end instead of an S, because this is not a solid electrode. It is tubular. So it's a flux core electrode. It's tubular. So you have an E for electrode still. So it's E, two numbers, a T, and then another number. E for electrode. This one, the first number is going to be the minimum tensile strength. The second number in this case, this is where it could get confusing. The second number in this case is the primary welding position for this particular electrode. So you're going to have a 0 or a 1. 0 being for flat or horizontal, and 1 means all positions. So if you have like a E70T electrode, for instance, which would be similar to our usual ER70S6. So if you had an E70T flux core electrode, that 7 is giving you the tensile strength. In this case, the 0 there is telling you this is only for flat and horizontal positions. So that is where the distinction comes in. That's important to remember. So again, the sort of like zoom back, and what you would first recognize if you see this electrode designation is that there's no R and there's a T here. So this is going to be, you can immediately say to yourself, this is for flux core. And then next one is a flux core electrode for low alloy steel. We've talked about all these different alloys that you can weld, and you have to have the right electrode to weld those particular alloys. So there's more information in this electrode. You still have the E, you still have two numbers, and you still have the T. So that again tells you, okay, this is a flux core electrode, but there's more numbers here, so it's going to be for an alloy steel here. So let's go through this one. E for electrode, X, the first number here is for the minimum tensile strength, just the same thing. Then the second one is for the welding position, the same thing. T for tubular flux core, same thing. Then you have this extra number here. This tells you about usability and performance capabilities. So how this can be used. And then this last X is the last number here is the chemical composition of the deposited weld metal. So you don't have to memorize, what each number means, for each chemical composition and all that stuff. It's just we want to try to remember, what these different pieces of information are so that we can figure them out when you need to figure it out. So as the zoom back, just immediate looking at it, you got an extra X here instead of this designation for carbon steel. So you can immediately look at, say, flux core, because it's got the T in it, and it's got an extra number, so it's low alloy steel. Those are the kind of things you want to be able to try to recognize quickly. And now our next piece of information, our next kind of electrode, this is for, again, sort of the step up in complexity, if you will, is an electrode for chromium and chromium steel. So these are particular specific alloys of steel. So this one, your zoom back is E and T, flux core, we got that. Okay, look at this, we got 3 numbers here in the middle. Now we know right away, okay, this is one of those chromium, steel, special weird things. And in this case, so what we're zooming in now, what it's actually telling you, E is for electrode, T is for tubular. These 3 numbers in here, this is the classification according to the composition of the electrode. So this tells you how this electrode is classified according to its composition. And then this last number back here, this last X, last symbol, last piece of information, if you will, that's going to tell you the type of shielding medium. So remember, with flux core, they can be self-shielded with no gas necessary, or you can also add gas to it and have both of those methods of shielding available. So you have 1 is for CO2, 2 is for a 98 argon, 2% O2. 3 would be for none, so this would mean it could be a self-shielded. G is not specified, so that would be sort of up to the welder or up to the welder's boss or engineer or whoever is deciding those things. All right, so those are some specifics of electrode composition there. Don't get too intimidated by all of that. Remember that sort of zoom out is what I want you to get, trying to be able to recognize quickly. Not every single piece of information, but just, oh, that's flux core, that's GMO, that's a MIG wire, those kinds of things. That's what I want you to recognize. Electrode material forms, the way that you can purchase them from your welding supplier. Usually you just have the spools like we do at OCC. Some of the spools are plastic. Some of them can be formed wire. You can even have wood ones. And you just kind of throw those away after you're done using them. You can also use these big drums. There's the wire is all spooled around in there, and then it just comes pulled out right here. That would be for extended use, like usually for robotic applications. You got a robot machine that's running a lot of welding quickly and just repeating the same thing over and over. So the way you want to treat your electrode material, you do want to try to prevent contamination. If you have a bunch of filler material spools that you buy, it's best to keep that material packaged for as long as possible. You don't want it sitting out, getting wet or just moisture or pieces of metal from grinding stuck on it and stuff. So keep it in the package. Cover it on the feeder. If some of those feeders are external, they're not contained in a box like the ones at OCC, so cover it in that case when it's not in use. You don't want to handle it a whole bunch. You get whatever grease and stuff you got on your fingers. When you're using, your welding gloves, you got all kinds of messy stuff on those gloves. So you want to try not to handle it with those dirty gloves. And work in a clean, dry area, especially. If your machine's going to be idle for a long time, it would be good to remove the spool, pull it out from the gun so it doesn't get, rusty or corroded or something in there. And of course, cover it up, put it away. And then do things like it's inspecting your drive rollers, the guide tubes in the inside of your gun, liners, contact tips, stuff like that when you're changing the spool out. It's good practice to kind of give a little cleanup if you can in there. Just keep stuff clean and tidy is just generally a better way to go. Now, if you are the one who is deciding which electrode you're going to use, at OCC you don't. We have all the electrodes there, and that's what you use. But if you are the one deciding, you would need to take into consideration the base metal that you're welding, if it's an alloy steel, chromoly steel, or just a mild steel, whatever it is. The mechanical properties, if you need it to be brittle, not brittle, strong, whatever, have certain kind of amount of tensile strength or whatever. The type of shielding gas that you are using, if that is required with your GMA or your flux core with gas. The type of weld joint that you're doing does come into play, especially for doing something like when you're using flux core, if you have to decide if it's going to be in the flat position or horizontal position. Remember, then there's certain electrodes that are designated for all positions or certain electrodes that are only for specific positions. So you'd have to keep that in mind when you're choosing your electrode. So the weld joint and the position of that weld. And then, of course, how it's going to be used. Is it need to be, again, like strong or impact resistance or heat resistant or, whatever however it's going to be used. So that was, again, moving through this equipment. You get a power source. I talked about the wire feeders and electrodes and stuff like that. And then we're going to talk here about shielding gas, specifics of shielding gas, and of course the regulator that controls the shielding gas here. Chapter 4, if you're following in your book. So regulating shielding gas. Everyone obviously has been doing this already in class. Now we're going to kind of break it down, talk about what it is exactly that you are doing. So the regulator, whatever it is, it's connected to your gas cylinder that feeds the gas into, to your machine and then basically out through the gun. That reduces the pressure from the cylinder to a desired level. That pressure at the cylinder is huge. It is, compressed gas in that cylinder. You can't just open it up and have it come, spraying out, basically. So the regulator basically, gives you the control over that pressure. So you can choose how much comes out at a time. The flow meter type regulator, there's two different kinds of regulators. So there's the flow meter type regulator, and then there's just this standard regulator here. So this flow meter type regulator, that is a little bit different in that it regulates the flow of the gas to the welding gun. So that's the flow of the gas out of the gas cylinder, not just the pressure. So it's a little bit more precise. If you do any TIG welding, all of the TIG welders, I'm pretty sure all of the ones we have at OCC have a flow meter instead of just a regulator, because you want more precision with TIG welding. With GMAW, it's not quite as important to be that precise, so you'll often see a lot of our machines still have these sort of standard regulator types that are regulating what you are controlling is the pressure. These flow meter types too, they can measure different types of gas. You'll see it marked on the side of the cylinder here. So you have to make sure when you're reading it that, if you have if you're welding with C25, which is mainly argon, that you're looking at the argon measurement, or if you're using a different gas, you look at the right measurement, because each gas has different masses. So it will move the ball differently. So you have to read it correctly. So what is flow versus pressure? Okay, so the correct gas flow for any particular weld, it depends largely on the nozzle size. Again, not something you have a lot of control over at OCC, and not something you really are going to be thinking about or changing a lot. You generally, you pick up whatever your supplies are for your gun at your welding store, and that's it, and you're good, and you use that. So because we don't have all of those controls, basically my sort of general idea, you start with 25 to 30 CFH. If you have a regulator that has CFH marked, that is cubic feet per hour. So that's the actual flow. Start somewhere around there and then adjust as necessary. So it's important to remember that too much gas can be just as bad as too little. So with too much gas, you can have too much turbulence. So you're kind of blasting a lot of gas out of your nozzle, and that is moving the air around it and ends up pulling in oxygen and other contaminants from the air around the weld and not properly shielding it from those contaminants. So that's flow. And then pressure, so flow is measured in CFH, cubic feet per hour. Pressure is usually measured in PSI, pounds per square inch. There's not a easy conversion from PSI to CFH. So if you have a regulator that's just measuring pressure, then you're going to set the pressure, and that's fine. It's going to be just fine. So different manufacturers, basically, they determine what your flow is going to be by the size of the orifice in the regulator. So this means it kind of has a set flow, and you adjust the pressure. I usually recommend starting at 15 to 20 and then adjusting as necessary for that. And remember, when you're looking at either a regulator or a flow meter, whatever it is that you're looking at, let's see, I wanted to go back. There we go. You want to look at things like, make sure that you're looking at the right part on the cylinder here. And for these regulator styles, the needle styles, there's usually 2 numbers marked. I know it's not super clear in the picture, but there's going to be these black numbers and these red numbers, and they're labeled. Sometimes they are measuring CFH or LCFH, liters, some other measurement. So you do have to make sure whatever you're looking at, whichever regulator you have, that you're reading the right reading on your regulator. So make sure next time you go into class to weld that you do take a look at those regulators and kind of make a point to look at it a little bit closer in a little bit more detail to make sure that you're understand what it is that you're reading and interacting with. Now, of course, the functions of the shielding gas. The main function would be to shield the electrode and the molten metal, the metal that you're melting in the base metal with because of the electricity that you're using. It shields all that liquid metal from the atmosphere. That's the main purpose of shielding gas. It also does, though, help to transfer heat from the electrode to the base metal. So that is another valuable function. It can help to stabilize the arc pattern. Helps to control the bead contour and penetration. It aids in the metal transfer, whatever the transfer mode. It can determine different transfer modes, remember, based on whatever gas you're using. When we did, or when we do spray transfer, you have to change it to pure argon or very high argon content to get spray transfer. It can also, the shielding gas can assist in the cleaning action, provide the wetting action. So there's all these different things the shielding gas does that actually do affect the quality of your liquid weld pool, the way that your electrode melts off, and therefore, in the end, the look and function of your actual weld bead. So shielding gas does more than just shield it from the atmosphere, but that is its main purpose. So now we're going to talk a little bit about the 2 different, we got flux core self-shielded and we got flux core gas shielded. So we're going to talk a little bit about those 2 real quick. Flux core self-shielded, also called open arc process, that you'll see the designation as FCAW-S often. So this means that the electrode has everything you need for shielding, and you don't need to use extra gas with it. So the flux, when it's heated, when it's burned, it creates its own shielding gas, and then it forms, of course, that protective slag coating as it cools to protect the weld, just the same as with stick welding. The benefit of this, the main huge benefit, is that it can be used outdoors because the wind can't blow the gas away in the same way. However, it does produce that slag, so then you have to chip it off, clean it off in between welds, and it produces a lot more smoke than GMAW, which can be hazardous to your health, obviously, and a problem if you're welding in certain indoor environments, especially. And then it's also less portable and requires more equipment than stick welding, than SMAW. But the benefit here, the reason why you might choose it instead of stick welding, is that it does have a much higher deposition rate. Basically, it's a faster process. With stick welding, you have your stick, you burn it up, you drop the stub, and then you pick up another stick and you burn it up. So that the stopping and starting, it takes up time. With flux core, it's just the same as with MIG welding. You press the trigger and you're welding. You don't have to have that replace your material all the time that you do with stick welding. Now with the gas shielded or dual shielded process, it's FCAW-G, G for gas. And this one usually, almost always, you use CO2 for shielding, alone or with argon. So this is for extra protection from contamination. It's an extra shield, basically. So you got the good deposition rates of any of the FCAW or GMAW processes, the good metallurgical aspects, metallurgical values, and then good visibility. You can make welds in all positions. It still does produce slag and more smoke than GMAW, and again, still less portable and more equipment than SMAW. Even more equipment, of course, than FCAW self-shielded, because you have to have your extra, the extra gas cylinder and the regulator and those things that cost more, and you got to lug them around. So talking a little bit about the commonly used shielding gases, we're going to go into those. This would be mainly for GMAW, of course, the one that mainly uses gas. So for GMAW, you can have more options available to you: argon, helium, CO2, oxygen, or different mixes of these. And then FluxCore, again, is just going to be CO2 or argon. So we're going to talk a little bit about these gases. This isn't the kind of thing, again, that you have to memorize all of these different aspects of these different gases. We just want to kind of get a quick introduction to them, have a little bit of information about them. So argon is an inert gas. It's cheap, easily available, used for GMAW, especially of non-ferrous metals. You'll do pure argon, like when you're doing aluminum. Or when I do bronze, I use pure argon. For FluxCore, you would mix it with CO2. You get narrow bead widths with pure argon, deep penetration, and reduced spatter and contamination. Those are the benefits it can give you. And then CO2 is a reactive gas. So the reason why we call GMAW gas metal arc welding instead of MIG, metal inert gas welding, MIG welding. The reason we call it GMAW is because we can use these reactive gases like CO2. And CO2 has become increasingly important for GMAW welding. So this actually combines chemically with the weld pool. That's what's meant by reactive. So you can use it alone. Usually it's in a gas mixture. It does have a little bit more erratic and harsher arc. That's why you'll usually use it in a mixture. When used alone, it produces more spatter. And you have to make sure, because there are different levels of CO2, you have to make sure it's a welding grade gas that you're getting. So these are mixes for ferrous metals. We're not going to talk about all these different mixes. This is the one I wanted to focus on. I've mentioned it many times before, C25. This is the gas that we use at OCC unless we're switching to pure argon for aluminum or spray transfer. So C25 is 75% argon, 25% CO2. That's why you have the C for CO2, 25 for 25%. And this is just a very standard welding gas. So then there's some other mixes. We're not going to go through all of those right now. So for the dual shielded or gas shielded FCAW, remember that you have that extra the determinant on the end of that electrode that tells you exactly what kind of gas you want to use or what mix you want to use. So if you are the one selecting the gas mixture, which you might be if you're working for yourself kind of thing, think about the mode of metal transfer, of course. So you have to make sure you use a high argon content if you're trying to do spray transfer. Your base metal type and thickness, of course, if you're not using just mild steel, you're getting into some of the alloys and stuff. You have to be more specific about your gas. The joint design and the weld position, again, filler metal composition and size, the chemical composition of the weld metal, and the quality of the weld metal. So just things that you would have to consider. Again, usually for the majority of your welding, you just go into your welding supply store and tell them you want some welding gas, and they'll give you C25. The way that you will get gas at your welding supply store can be in flasks like this, but that would be just for like large-scale manufacturing kind of purposes. Usually you'll get them in these cylinders of different sizes, and they have letter designations for the different sizes. You can see what the sizes mean here in this chart, which is in your book. An important note about safety here. Gas cylinders always should be stored outside or in a well-ventilated area just in case they start leaking. They should always be stored upright, very important, and they should always have that safety cap in place, again, as a just in case. To keep them upright, they should be secured to a rigid support, something solid, and they should be chained to that, not with straps. The idea being that, straps could get accidentally cut if they come into contact with something sharp, or they could, of course, get burnt if, something dramatic happens. So a chain will be more stable to keep those up in place. The type of mixture should be properly and clearly identified on the label. Follow all the safety precautions. And then remember, inert gas, like argon, the leaks can't be seen, can't be smelled, can't be tasted. So that's why it can be dangerous, because the gas can be leaking and you have some kind of flammable gas filling up a space, which could be problematic. So they are an important, there is important safety considerations with these things. A little trick here for testing for gas leaks. It's often something that you might hear or you might feel, somewhere that there's like a stream of gas coming out, but it can be hard to detect leaks. I don't know if anyone's ever had a bicycle where they try to find a leak, but this is a similar process for this. You can use a bubble solution like this, or just basically some water and soap mixed together. You could spray on it, or even Windex also works in the same way, because whatever you have some kind of substance that bubbles, and that gas is going to create more bubbles, so you'll be able to see where those bubbles are forming, and then you can see where the leak is and fix it. And then the markings on a cylinder, you can, again, this is another thing you can kind of take a look at next time you're in class. And if you have any questions, we can take a look, and I can try to show you some of the markings on here. But the important thing is there's lots of like letters and numbers and a lot of information here. But the important thing is that they have a date on them. And that date is good for 5 years standard. So if it's past 5 years, it has to be recertified, retested to make sure it's still sound and safe. If you have a star on it, you'll see that means it's good for 10 years. But the reason why this is important is, of course, so that your cylinders you're getting are tested and safe and within the regulation safety requirements and everything. But if you are buying a cylinder, is either like off from somebody else or even from your welding supply store, it's a good idea to check and double check that, find that date and see, where it is in those 5 years or 10 years, so that you're not getting too old of a one. If it does, you will probably eventually get one that has to be recertified, and that's fine. You should just be able to take it back to your welding supply store. They'll take a look at it and notice it needs to be recertified. You pay an extra fee. It's usually not too much, and then you'll get another cylinder back that is within specification, and you'll go on about your life. There's a couple of charts here in the book that I think are useful. This can be just kind of a look through again a little bit more on your own time, giving you some different advantages for different kinds of gas for different things to help you make those decisions. Recommendations for spray transfer, and some other recommendations for different applications. So that is it for that show or that slide presentation, my lecture today. As always, with any questions, you can always email me, or we'll talk on Thursday if you're watching this sometime before Thursday. And I will see you in class. All right. See ya. Bye.